It drifts quietly in the southern sky, a pale ember lost among brighter neighbors. To most telescopes, it is unremarkable, faint, steady, ordinary. Yet this single point of light, known as HD 140283, may be older than the universe we thought we understood. Astronomers call it the Methuselah Star, a celestial contradiction that dares to be older than time itself. When scientists first calculated its age using parallax data from Hubble and stellar evolution models, they stopped cold: 14.46 billion years. That number did not belong in any equation. The universe itself is only 13.8 billion years old. How could a star exist before the cosmos that birthed it? The answer lies in its chemistry. Methuselah is made almost entirely of hydrogen and helium, with scarcely a trace of heavier elements. Astronomers call this extremely low metallicity, a chemical fingerprint from the earliest epoch, when the universe had yet to forge carbon, oxygen, or iron in the hearts of dying suns. Every atom inside it tells a story written moments after the Big Bang. It is a fossil of the first light. To understand why this discovery shattered cosmology, we have to step backward in time to the universe's first few 100 million years, when matter cooled from plasma into clouds of pure hydrogen. Those clouds collapsed under gravity, igniting the first generation of stars, the population 3 stars. They lived violently and died young, enriching space with the metals needed for the next generation. Methuselah, however, doesn't fit that lineage. It seems to have formed from material too pristine, too early, and somehow survived every cataclysm that followed. When researchers recalibrated their models adjusting for uncertainties in distance, brightness, and composition, the paradox softened but never vanished. Even with generous margins, the age settled near 13.7 plus or minus 0.7 billion years. That means the Methuselah Star may have kindled its light a few 100 million years after the Big Bang, long before the Milky Way took shape, before Earth's atoms even existed. And so, hidden in the quiet constellation Libra, a lonely subgiant carries within it the memory of creation. It is not merely old, it is ancestral. Its light traveled 190 years to reach us. Yet its story reaches back to the first flicker of cosmic dawn. If a single star can outlast our models of time, what else might be older than we dare imagine? What truths still lie buried in the night, waiting, like Methuselah, to remind us that the universe has not told its whole story? Before Methuselah, there were other stars that no longer exist, erased by time before galaxies had names. They were called population 3 stars, and they were the universe's first children, born when darkness still outweighed light. They illuminated the cosmos for the first time and then died so completely that only their absence remains. In the beginning, the universe was simple: hydrogen, helium, and a trace of lithium, nothing else. The elements of life, carbon, oxygen, iron, didn't yet exist. When gravity drew the first clouds of hydrogen together, it created giant stars hundreds of times the mass of our sun. Their lifespans were brief, some lasting barely a few million years, but in those short lives, they forged everything that would follow. They were furnaces of creation, fusing pure hydrogen into the heavier atoms that would seed future worlds. Their deaths were spectacular. When their fuel ran out, they collapsed and exploded as pair instability supernovae, scattering the first metals into the void. That dust became the foundation for galaxies, planets, and eventually, people. Every atom of iron in your blood, every carbon chain in your DNA was once part of one of those first explosions. And yet, no one has ever seen a population 3 star. They are theoretical ghosts predicted by physics, confirmed only by their fingerprints in the chemistry of younger stars. That's where Methuselah comes in. Its near absence of metals makes it a messenger from that vanished era, perhaps even a direct descendant of those first suns. In its spectrum, scientists read the residue of creation itself: hydrogen unspoiled, helium untouched by fusion. It's the kind of star that shouldn't survive in a galaxy so old, yet somehow it does. The first stars changed everything. Their ultraviolet light reionized the universe, turning the cosmic fog transparent and letting light travel freely for the first time. They built the scaffolding upon which all galaxies would form. Without them, the night sky would still be dark, filled only with silent gas and unshaped potential. But the universe forgot their names. Their ashes were mixed into new generations of stars, their light stretched beyond visibility. Methuselah is one of the last whispers from that epoch, a survivor forged from the purest matter, living long past its kin. While others burned themselves out in fury, this one endured in restraint, fusing hydrogen at a measured pace for billions of years. Today, when we peer at its spectrum, we're not just looking at an old star, we're witnessing a bridge to a time before time, a relic of a universe learning how to make light. The age of the universe is one of the few numbers in cosmology that feels sacred, 13.8 billion years, derived from the light of the cosmic microwave background, the expansion rate of space, and the fingerprints of the earliest elements. It's a cornerstone of modern physics, one of the most carefully cross-checked figures in science. And yet, one small star, Methuselah, seems to whisper something different. When astronomers first calculated HD 140283's age at 14.46 billion years, the universe's math broke down. No star should be older than everything that exists. At first, it seemed like a measurement error, the kind that disappears under better instruments or sharper equations. But even after decades of refinement, Methuselah's age hovers dangerously close to the universe's limit. If its true age lies at the upper end of the margin, 13.7 or 13.8 billion years, then it was born within cosmic minutes of the Big Bang itself. How could that be? The answer might lie in the way we tell cosmic time. The age of a star isn't measured by counting its rotations or tracing its orbit. It's derived from stellar evolution models, equations that describe how stars burn their fuel. The more hydrogen they have, and the faster they fuse it, the brighter and shorter their lives. Methuselah's faint glow means it burns hydrogen slowly, an introvert among stars, conserving its fuel like a candle refusing to die. But stellar models rely on assumptions about temperature, metallicity, opacity, and convection. A single miscalculation can shift a star's estimated age by hundreds of millions of years. When astronomers refined their data using parallax measurements from the Hubble Space Telescope, the distance to Methuselah became more precise, and its luminosity slightly lower. That alone could reduce its estimated age, but only by a fraction. Even then, the result remained unsettling, nearly as old as the universe itself. Some physicists proposed a different approach. Maybe the universe's clock is wrong, not the stars. If our estimates of the Hubble constant, the rate at which the universe expands, are even slightly off, the cosmic age could shift. Recent tensions between different measurements of that constant, the so-called Hubble tension, suggest that our cosmic clock might indeed be running fast or slow, depending on how we read it. This tug of war between observation and theory has left cosmology in a quiet crisis. If Methuselah truly predates the Milky Way, it forces us to re-examine the very framework of cosmic chronology. Maybe the Big Bang was slightly older than we think. Maybe new physics unknown particles, alternate inflation models, or variations in dark energy could stretch the universe's age just enough to fit the anomaly. But there's also a more poetic answer. Maybe Methuselah isn't defying time. Maybe it's reminding us that time itself is elastic, that the universe's story isn't written in a single timeline, but in overlapping layers of expansion, fusion, and decay. In the end, whether this star is truly older than the universe or simply at its edge, it holds a message far deeper than mathematics, that even in a cosmos built on precision, there is still room for mystery. Every star carries a timestamp written not in numbers but in elements. The universe keeps time through chemistry. Astronomers call it metallicity, the fraction of a star's mass made up of elements heavier than helium. To the untrained eye, metals may sound trivial, but in the cosmos, they are the fingerprints of history. Every generation of stars leaves behind its ashes, carbon, oxygen, iron, enriching the gas that forms the next. The more metals a star contains, the later it was born in the cosmic story. Methuselah, however, tells a different tale. Its spectrum, those thin, colored lines of light, reveals an almost pristine composition. It is what astrophysicists call a population 2 star, ancient, but not quite the first. Its metal content is less than 1,000th that of the Sun, which means it formed in an era when the universe had barely begun recycling its matter. This low metallicity is not just a clue to its age, it's a chemical confession. Methuselah was born in a universe still young enough to remember silence. To read a star's chemical clock, scientists spread its light through a prism and measure the depth of its absorption lines, tiny dips where elements steal photons at specific wavelengths. Hydrogen and helium dominate, as expected, but iron, magnesium, and oxygen appear in whisper-thin traces, like faint brushstrokes left by the first supernovae. Each ratio between these elements is a signature of cosmic ancestry. Too much oxygen, and the star formed from the remains of a single massive explosion. Too much iron, and it was forged in a later age after many generations of stellar death. Methuselah's chemistry is a paradox. Its oxygen-to-iron ratio suggests it was born in a universe freshly seeded by the first supernovae when the cosmos was still less than 500 million years old. Yet, its temperature and luminosity indicate a star that has been burning steadily for nearly 14 billion years. It shouldn't exist in this equilibrium yet. There it is, balanced delicately between history and impossibility. This is why astronomers refer to metallicity as a cosmic calendar. Each atom is a memory, each element a page. Stars like Methuselah allow us to reconstruct the genealogy of matter, to trace the flow of creation from the Big Bang to the present. When we analyze its light, we are reading the autobiography of the universe itself, encoded in a single star. But the real beauty lies in what's missing. Methuselah's scarcity of metals means it predates the chemical abundance that made life possible. In its youth, there were no rocky planets, no carbon-based molecules, no complex chemistry to sustain biology. It lived in a cosmos of simplicity, a time before diversity. If our sun is a storyteller, Methuselah is a witness, a relic of the universe's first wordless dawn. The more precisely we decode its elements, the more it teaches us that the universe evolves not just through time, but through transformation. The atoms that once belonged to the first stars now live in every breath we take, every heartbeat, every planet, orbiting every Sunday. Methuselah reminds us that cosmic history is not written in stone, it's written in starlight. And somewhere within that faint yellow glow lies the universe's first calendar, its chemistry still ticking, its memory still burning, long after the first age ended. For most of modern cosmology, the age of the universe felt settled, a triumph of precision born from countless observations, 13.8 billion years. Not a round number, but a sacred one. It was the product of harmony of equations that matched the expansion of space, the glow of the cosmic microwave background, and the chemistry of the oldest stars. Then came the cracks. Methuselah wasn't the first star to challenge cosmology, but it became the symbol of a deeper conflict, a quiet war between the ways we measure time itself. On one side stands Planck, the European Space Agency's mission that mapped the cosmic microwave background in exquisite detail. Its data paints a universe with a specific rate of expansion, the Hubble constant, measured at about 67.4 kilometers per second per megaparsec. From that rate, the universe's age follows naturally, roughly 13.8 billion years. But when astronomers measure the Hubble constant directly using supernovae, variable stars, and distant galaxies, they get a faster number, closer to 73. That may seem like a small difference, but cosmically, it's enormous. A faster expansion means a younger universe, one closer to 12.5 billion years. And that's where the paradox deepens. If the universe is younger, then Methuselah's age isn't just unusual, it's impossible. This tension has become known as the Hubble crisis, not a breakdown of physics, but a sign that something fundamental is missing. Are our models incomplete? Are there unknown forms of energy or particles that altered the universe's early expansion? Or is light itself deceiving us, warped by phenomena we don't yet understand? Some theorists propose an answer in the early dark energy hypothesis, a brief, unseen burst of repulsive energy that may have accelerated the universe's infancy, changing how we perceive its age today. Others look to new physics entirely, exotic neutrinos, quantum fields, or even the possibility that the laws of gravity behave differently across cosmic epochs. Each solution stretches our understanding further, yet none resolves the puzzle completely. Methuselah's existence lives at the heart of this tension. If the star's age remains valid, it suggests either our cosmological clock runs fast, or that the universe's earliest conditions weren't uniform. Perhaps time itself moved differently in the first moments after the Big Bang, flowing unevenly across regions of space as the cosmos expanded and cooled. Even within the star, small uncertainties remain. Tiny variations in metallicity, luminosity, and distance can change the result by hundreds of millions of years. But the problem refuses to vanish. Each refinement of our instruments only sharpens the mystery. The deeper we look, the more the universe seems to disagree with itself. The equations that once fit perfectly now drift apart like galaxies in an expanding void. Somewhere between the first stars and the edge of the cosmic horizon lies a secret one that could rewrite our understanding of both time and creation. The Methuselah Star doesn't just challenge astronomy, it exposes a truth we often forget: that the universe is not a solved equation. It's a conversation still unfolding, and sometimes the silence between answers says the most. In the violent youth of the cosmos, survival was rare. The first stars, massive, unstable, and short-lived, burned themselves to ash in a matter of millions of years, seeding the void with the elements that would make everything else. They were brilliant, but doomed. The smaller ones, however the quiet ones, had a different fate. Methuselah belongs to that second kind. It is a survivor from an age when most of its peers died long ago, a low-mass subgiant star that somehow slipped through the cracks of cosmic extinction. To understand how it endured for nearly the entire history of existence, we have to look inside it, into the delicate balance between gravity and fusion that determines whether a star lives or dies. Stars are born from collapse. Gravity pulls hydrogen together until the pressure and heat at the core become so extreme that atoms fuse into helium, releasing light and heat in the process. But every star lives by a fragile truce: the outward push of fusion against the inward pull of gravity. When fusion slows, gravity wins, crushing the core and igniting new, hotter reactions: helium, carbon, oxygen, until there's nothing left to burn. Massive stars burn their fuel in a cosmic sprint. Methuselah, by contrast, chose to walk. With only about 80% of the sun's mass, it burns hydrogen with incredible restraint. Its low metallicity means fewer heavy elements to trap heat, allowing energy to escape more efficiently. That keeps its core cooler and its fusion slower, extending its lifespan far beyond the universe's most common suns. While giants lived and died in blazes of creation, Methuselah dimly persisted, quiet, patient, and almost invisible. This combination of lightness and purity made it nearly immortal by stellar standards. When it was young, galaxies were still merging, and radiation from newborn quasars flooded space. Entire star clusters were torn apart by gravity, but Methuselah's relative isolation protected it. Unlike stars born in dense galactic hearts, it likely formed in a primitive region of the Milky Way's halo, a stellar outskirt where collisions were rare and time moved slowly. It was born far from chaos, and that distance became its salvation. Today, Methuselah has reached the subgiant phase, the slow transition between hydrogen burning and the helium fusion that signals old age. Its light is soft, yellowish-white, just slightly cooler than the sun's. In another few billion years, it will swell into a red giant, shed its outer layers, and fade into a white dwarf, a faint, cooling ember in the dark. But until then, it remains one of the oldest active sources of light in the known universe. It shouldn't still be here. The galaxies it has drifted past have changed shape. The cosmic web itself has evolved, yet Methuselah persists, crossing epochs as if time were a gentle current instead of a flood. It has seen the Milky Way grow arms, the first planets form, and entire civilizations rise on one small blue world orbiting a younger star. Its survival isn't just luck, it's physics refined into poetry. It shows that endurance in the cosmos isn't about power, but balance. The mightiest stars burn out, while the faint ones endure. Methuselah's quiet defiance is a cosmic reminder. Sometimes, to last forever, you must live slowly. And so, as the universe stretches toward entropy, one small sun continues to shine a solitary witness to the dawn of time, and perhaps the last to remember it. Methuselah drifts through the Milky Way like an exile, ancient, unanchored, and almost alone. Its orbit is not the calm circle of a star born in the galactic disk, but a wild, elongated path that cuts straight through the heart of the galaxy and back out into the darkness. Each loop takes thousands of light years and hundreds of millions of years to complete. It doesn't belong to the spiral arms or the glowing plane where new stars are born. It lives in the halo, a vast, invisible sphere of space surrounding the Milky Way, populated by relics of creation's earliest days. This orbit tells a story as old as the galaxy itself. The halo is not a tranquil place, it's a graveyard of collisions. Long before the Milky Way took its present form, it was built from countless smaller galaxies merging together, their stars torn apart and scattered into vast, ghostly streams. Methuselah likely came from one of those first galaxies, a fragment that was swallowed by ours billions of years ago. When that ancient system was destroyed, its stars were cast into wandering orbits, forming the Milky Way's halo. Methuselah is one of those survivors, still tracing the silent memory of that cosmic cannibalism. Its path takes it both above and below the galactic plane, sometimes 10,000 light-years from the center, sometimes 50,000. At its furthest point, the glow of the Milky Way would fade into a faint ribbon across the sky. Out there, the galaxy is just a structure of light hanging in the dark, fragile and small compared to the emptiness around it. For billions of years, Methuselah has moved through this solitude, untouched by the chaos of stellar nurseries or the violence of supernovae. It's as if the universe itself placed it in orbit beyond danger to endure as a record of what came before. When astronomers tracked its motion precisely using data from Gaia and Hubble, they found something extraordinary. Methuselah's orbit isn't random. It's retrograde, moving opposite to the rotation of the Milky Way. That single detail reveals its foreign birth. It wasn't formed here, it was adopted. Somewhere, long ago, an infant version of our galaxy collided with another, and Methuselah was captured in the aftermath. That makes it older than the Milky Way's spiral arms, older than the structure we call home. When astronomers look at Methuselah, they're not just studying a star, they're reading an artifact older than memory itself. Its light is more than illumination. It's a fossil record. Every photon it emits carries a trace of the conditions that existed when the cosmos was young, when galaxies were still forming, and the first heavy elements were being forged in stellar cores. Light travels at a constant speed, and that means every beam is a message from the past. When we observe Methuselah through a telescope, we aren't seeing it as it is now, but as it was 190 years ago, the time it takes for its light to reach us. But what truly makes this star a time machine isn't just its distance, it's its composition. Methuselah's chemical fingerprint is a direct window into the first few 100 million years after the Big Bang. Using spectroscopy, the science of decoding light, astronomers can dissect a star's atmosphere and see the story written in its elements. Methuselah's spectrum is astonishingly simple. It's made almost entirely of hydrogen and helium, the universe's first two elements, with only trace amounts of heavier atoms like oxygen, calcium, or iron. That near-pristine makeup is the unmistakable signature of Population 2 stars, the second generation, born from the ashes of the first. The first stars, known as Population 3, were made of pure hydrogen and helium. They lived fast, died young, and seeded the cosmos with the heavier elements that make up planets and life. But none of those first stars remain. They were too massive, too volatile, their lives ending in colossal supernovae or direct collapse into black holes. Methuselah, however, was born just after that era from the first clouds of gas enriched by those ancient deaths. Its chemistry carries the faint fingerprints of that first generation, the ashes of the first suns ever to burn. In this way, Methuselah is a cosmic archive. Its atmosphere has remained almost untouched since the dawn of time. Unlike planets or living worlds, it doesn't evolve chemically. It doesn't mix or renew itself. Every atom in its spectrum is a preserved clue, a relic of the universe's youth that has drifted through space for 13 billion years without erasure. When scientists analyze its light, they are effectively running a forensic test on the cosmos itself, studying how the early universe transitioned from simplicity to complexity. What they found is that Methuselah's existence perfectly bridges the gap between two epochs: the primordial universe ruled by hydrogen and helium, and the structured, star-filled cosmos we inhabit today. Its low metallicity confirms that it was born before the Milky Way reached chemical maturity, before supernovae had painted the galaxy with the full palette of elements. It's like finding a living dinosaur, breathing and burning quietly, while surrounded by descendants that have evolved for billions of years. That makes Methuselah not just a star, but a reference point, a calibration mark for everything else. By comparing its light to younger, metal-rich stars, scientists can trace how each generation added new elements to the interstellar medium. This gives us the cosmic genealogy of matter, the slow accumulation of ingredients that would one day form planets, oceans, and biology. Every photon Methuselah emits today began its journey long before humans existed, before the Earth existed, carrying within it the encoded memory of creation. To measure that light is to hold a fragment of time itself, a whisper from an age before galaxies learned to shine. In the end, that's what makes Methuselah so extraordinary. Not its paradoxical age or its improbable endurance, but the fact that it is still telling the story of the universe's beginning not as myth, but as measurable truth written in starlight. It is the cosmos speaking in its oldest language, the language of light that remembers. When Methuselah was first measured, its very existence seemed to mock the laws of cosmology. The numbers didn't lie, or so it seemed. A star estimated at 14.46 billion years old, shining within a universe believed to be 13.8 billion years old, created an impossible paradox, a child older than its parent. For years, scientists wrestled with this contradiction, a quiet but profound crack in our understanding of time itself. But the universe is rarely wrong, only our instruments are. The key to resolving the paradox lay not in rewriting the age of the cosmos, but in understanding the delicate machinery behind stellar dating. Determining a star's age isn't as simple as reading a clock. It's a symphony of variables: temperature, luminosity, metallicity, mass, and distance. Each must be measured with near-perfect precision, and even a tiny uncertainty can skew the results by hundreds of millions of years. Methuselah's age came from models built on these parameters, but each one carried its own margin of error. When the Hubble Space Telescope remeasured its distance using parallax, the tiny shift in the star's position as Earth orbits the Sun, The new data refined its luminosity and temperature. The result: its age dropped from an impossible 14.46 billion years to a more plausible 13.7 plus or minus 0.7 billion years. Still breathtakingly old, but no longer older than the universe itself. Even then, the mystery wasn't entirely solved. That plus or minus 0.7 billion year uncertainty still brushed against the universe's age, hinting that the story wasn't finished. Around the same time, cosmologists were re-examining the Hubble constant, the rate at which the universe expands. Different methods gave slightly different answers. Measurements based on the cosmic microwave background suggested an older universe, while those based on supernovae implied a younger one. The two results refused to align a tension now known as the Hubble discrepancy. And that's where Methuselah became more than an outlier. It became a test. If the star truly was older than expected, perhaps it was pointing toward a deeper correction in our cosmic timeline. Some scientists suggested that the universe might actually be slightly older, closer to 14 billion years, if the expansion rate were just a bit slower than current models assume. Others proposed that the apparent conflict revealed subtle physics missing from our equations, perhaps dark energy evolving over time, or new interactions within the earliest moments after the Big Bang. In a strange way, the paradox turned from a problem into a probe. By existing on the edge of cosmic possibility, Methuselah forced cosmology to refine itself. It reminded scientists that even the most elegant equations must bow to observation. It also underscored the fragility of our cosmic measurements, how every decimal place in the Hubble constant, every assumption about metallicity or temperature, reshapes the way we perceive time itself. Ultimately, Methuselah did not overturn the age of the universe. Instead, it illuminated its precision. It showed that the early cosmos could form stars astonishingly quickly within the first few 100 million years after the Big Bang. It proved that ancient stars still wander the Milky Way, carrying the record of that primordial dawn. And most importantly, it forced us to confront the philosophical edge of science, that every number we assign to the cosmos is, in the end, a reflection of our own limitations. The paradox was never truly about the star being older than the universe. It was about us, about how close we can come to truth when staring across eternity. Methuselah didn't break cosmology, it clarified it. And so, rather than contradicting the age of the universe, it affirmed something deeper, that the first light arose almost immediately after the darkness. That time, even at its beginning, was restless, and that the universe, from the moment it began, wasted no time at all in creating its oldest witnesses. For all its mystery, Methuselah remains a simple thing, a quiet, faint star still burning hydrogen into helium, its nuclear heart steady and calm. It has no planets, no moons, no life orbiting its light. Yet, in its endurance, it tells one of the most profound stories in existence. Against all odds, it has survived every cosmic upheaval from the birth of galaxies to the rise of our own civilization without being torn apart, consumed, or forgotten. Every atom inside Methuselah has been part of the universe since its first moments. That makes it a kind of living chronicle, a being older than our world, older than the structures that define space itself. It has watched the Milky Way form around it, watched the spiral arms twist into shape, and seen generations of stars flare, fade, and collapse into darkness. Through all of it, Methuselah kept shining, a reminder that longevity in the cosmos is not a miracle, but a kind of quiet defiance. When we talk about time, we often think in human terms, minutes, years, lifetimes. But Methuselah forces us to think differently. Its story compresses the age of everything we know into a single existence. While life on Earth evolved from single cells to consciousness, Methuselah simply endured. When our species emerged, it was already ancient. And when our species is gone, it will still burn for billions of years more, slowly fading but never collapsing violently. It's a star built not for brilliance, but for patience. In the far future, when the last galaxies drift apart and the night sky grows empty, stars like Methuselah will be among the final lights left burning. Their lifespans stretch deep into the future, long after our sun is dust and the Milky Way itself is unrecognizable. This star, once a paradox, becomes a metaphor for existence itself. It shows that survival in the universe is not about strength or dominance, but balance. The same traits that make it dim its low mass, its slow burn, are what grant it near immortality. Methuselah will never explode as a supernova or collapse into a black hole. It will simply cool, dim, and fade into a white dwarf, a quiet ember that will outlast entire galaxies. In this, there's an echo of our own condition. Civilizations, like stars, burn bright and brief. But endurance, the ability to persist quietly across ages, is what truly defies entropy. Methuselah embodies that endurance. It reminds us that meaning isn't always found in intensity, but in longevity. That sometimes the oldest light shines not because it is strong, but because it never gave in to chaos. And so Methuselah continues its lonely journey through the galactic halo, circling the Milky Way in silence, watching the slow unraveling of cosmic history. To the human eye, it's nothing special, a dim, unblinking star in the constellation Libra. But to science, it's proof that memory exists even in the language of physics. That time, while relentless, also preserves its oldest children. Someday, long after the last humans are gone, some distant civilization, perhaps not even born of our universe, might look toward this faint light and wonder what stories it carries. They'll measure its spectrum, trace its path, and see what we once saw, that this single point of light has outlasted everything that named it. Methuselah is the universe's quiet witness, not immortal in the literal sense, but eternal in meaning. It outlived the galaxies that birthed it and survived the mistakes of our calculations. It stands as proof that the universe is older, wiser, and more patient than we ever imagined. In its glow lies a lesson for us, that even in a cosmos built on decay, endurance is possible. That time is not only a destroyer, but also a keeper, and that somewhere, beyond the noise of our brief civilization, an ancient light still burns, carrying the first story ever told, waiting for someone to listen again.